We present NOCaL, work where we perform calibration-free semi-supervised learning of odometry and camera intrinsics. So vision has become a critical sense in modern robotics. Enormous advancements have been made in recent years to better utilize cameras for almost every task a robotic platform might be asked to do. There are a multitude of emerging imaging technologies that could benefit robotics. However, the need for bespoke models, calibration, and low-level processing represents a key barrier to their adoption, as this calibration and interpreting is often skilled and time-consuming work. An assumption is also generally made of static camera characteristics, but with devices that change due to vibration, temperature, along with needing to replace or upgrade cameras over time, recalibration is often required to maintain top performance. This makes both integrating new cameras and managing fleets of robots an onerous and complex task. To aid in this, we propose NOCaL, a framework that takes uncalibrated image pairs and jointly learns odometry, camera parameters, and visual appearance in an end-to-end fashion. This framework generalizes to a large range of cameras that can be modeled through a pinhole projection model and a freeform distortion map. In this work, we look at the task of odometry. Previous work has shown that we can learn odometry in a completely unsupervised fashion by taking frames collected over some trajectory and then jointly learning a pose and depth estimation. A prediction of the second input frame can be obtained by warping the first frame using this pose and depth estimations. A supervisory signal can then be obtained by minimizing the photometric error between the predicted and captured frames. So this works well, but using a warp function does struggle to deal with some of the more complex behaviors of light, as well as dealing with occlusions and limits some of the usable cameras that we can do. So in this work, we propose utilizing recent advancements in neural rendering techniques, which have been shown to produce outstanding results for novel view synthesis. One limitation of using neural radiance fields is that each rendering network can only render a single scene. However, when training odometry, it requires it to be trained across multiple. We're able to address this issue by using a hypernetwork structure, as demonstrated by Sitzmann's light field network, which enables a network to produce a renderer for a specific scene based on some latent encoding. Here is an overview of NOCaL. First, the input pair is fed through the encoding network that learns to produce a latent scene encoding and an estimated pose between the frames. The hypernetwork takes this scene encoding and learns to produce the weights of a light field network that represent these input images. These weights can then be injected into the light field network, which can be queried with a set of rays that correspond to the cameras at the input images. Because this process is fully differentiable, it means that we are able to backpropagate through the light field network to optimize the camera rays themselves, allowing us to learn the camera parameters along with the odometry. We use an implicit distortion model along with the learnt camera intrinsics to model the camera. We do utilize a small amount of label data throughout the training process to aid in the optimization, while also allowing the network to learn metric scale by utilizing some semantic information within the scene. Ultimately, allowing for the joint optimization of odometry, camera parameters, and view synthesis in a semi-supervised fashion. We demonstrate the results for the proposed system on both captured and synthetic data. The real-world dataset used was part of the Learn Light Field Odometry dataset from our previous work, which contains 45 separate scenes and camera trajectories. This was captured using a robotic arm, thus providing us with accurate ground truth data to test the generalization capabilities of NOCaL. The framework is able to produce novel views of scenes it has not been trained on. The reconstruction shows convincing results that the network is able to learn the 3D structure of the scene as it can show parallax. It has, however, lost some of the high frequency content that was originally there, though the reconstruction quality is not the critical measure here, but rather how well these renderings can predict the motion between the frames to aid in the learning of odometry. NOCaL is able to recover accurate camera intrinsics close to the ground truth values and those attained by traditional methods. We note that while our method is able to significantly reduce the error in the case of large distortion, the featured camera model used by Colmap does provide a better approximation. We compared NOCaL to two other odometry methods, a fully supervised approach that uses labeled imagery, and an unsupervised approach based on the previous work that requires the cameras to be calibrated and images rectified. Our zero calibration approach outperformed both the unsupervised and supervised methods, which means our framework must be benefiting from the large amount of unlabeled data. In this work, we present NOCaL, a framework that learns visual odometry in a semi-supervised way, without needing to calibrate the cameras beforehand. In future work, we aim to use a general camera model that can accommodate any camera geometry, not just the ones that are well represented as a pinhole. This work is the first steps towards a more general approach to using sensors on robotic platforms, with the goal to be able to plug and play different cameras without the complex task of learning how to calibrate and interpret them.